We're going to break down and talk about some of the features of the substitution reaction, and as we do this, we're going to be able to differentiate what things we need to undergo an SN1 reaction versus what we need to undergo an SN2 reaction, and we'll figure out how to differentiate the mechanisms. So first, let's look at the organohalide. That is your RX group. Most importantly, this carbon bonded to the X must be sp3 hybridized. Here are a few examples. So in this first one, this carbon is sp3, so that reaction will work, or that organohalide will work in a substitution reaction. On the second one, this carbon is sp2, so that will not work in a substitution reaction. And on the third one, the carbon with the halogen is sp, and again, that one won't work in a substitution. So you need this carbon to be sp3. Now you can have sp2 or sp carbons further out in your structure. We're focused on the carbon with the halogen attached. The second thing has to do with the substitution of the organohalide. Here's a series of different organohalides that we can use in substitution reactions. In all cases, the halogen is bonded to an sp3 carbon. Just to remind you of the classifications here, first we have a methyl halide, then we have a primary, secondary, allylic, benzylic, and tertiary. And what we find is that in terms of the mechanism, the methyl and primary halides can only do SN2 reactions. These will not undergo SN1 reactions. The tertiary halide will only undergo SN1 reactions. And then the three in the middle, secondary, allylic, and benzylic, these will undergo SN1 or SN2. So when we start to look at reactions and conditions to figure out a mechanism, it's these three that are going to be the most work for us because we're going to have to choose between mechanisms from other factors. So we'll be using the nucleophile and the solvent to help us determine the mechanism. Whereas with methyl and primary, these will only undergo SN2 reactions, at least in the realm of substitution, and then tertiary will only undergo SN1 reactions. Now, later in the chapter, when we start to incorporate eliminations, then we're going to have to consider that as well. Let's take some time to discuss why these particular substrates have the mechanistic preference they do. Why can these only do SN2? Why can this only do SN1? To answer this question, we're going to start with the SN2 reaction. And in the SN2, the nucleophile is involved in the rate determining step, and it must be able to fit. So if you compared an SN2 with a methyl halide versus a tertiary halide, think about what's happening here. So I'm going to draw my nucleophile, and in terms of the methyl halide, it's not a huge amount of stuff going on here. We just have the methyl group, so it's fairly easy for the nucleophile to come into this carbon and add and displace the leaving group. But in the case of the tertiary halide, now we have three methyl groups. Those each take up space, and really they're even bigger than the orange circles I'm drawing. What those do is kind of block out around the carbon. So that means it's really difficult for the nucleophile to squeeze in here to react. So you try to do that, it just can't get into that carbon, and it's often said that the carbon is too sterically hindered. So basically, think about this carbon here as your quarterback, the X being the football. Well, the methyl groups are a really good offensive line protecting this quarterback from the defense coming in to sack the quarterback. So substitution slows down SN2. So for the rate, the methyl halides are the fastest, followed by primary, then secondary, and then basically tertiary isn't going to react. Now, how about the SN1 reaction? So the SN1 is a completely different reasoning. For SN1, we need to be able to form a carbocation. So things that stabilize a carbocation is going to help that mechanism. So again, let's compare our two extremes. We'll just do methyl chloride versus tert-butyl chloride. And if you lose a leaving group in both cases, the methyl halide would give you a methyl cation. If you lose it from the tert-butyl halide, you get a more substituted tert-butyl cation. So in this case, we have tertiary versus methyl, and you already know a lot about carbocation stability. The tertiary is more stable and conform. So now in terms of the SN1 rate, the guiding factor is carbocation stability. Tertiary is the best, secondary will work, and then that's much better than primary and methyl. Where primary and methyl really don't go by SN1 reactions. So the allylic and benzylics, like secondary, fall under both mechanisms. And the reason for that is in terms of the SN2, even though this is allylic, this is still just a primary carbon in this case. So this is primary allylic. So that isn't an incredibly hindered carbon, so it's really no problem for a nucleophile to come in and attack that carbon. So that will come in, displace your leaving group, and that's your SN2 mechanism. For the SN1, although it's primary, it's not nearly as bad as a typical primary because when you lose this leaving group, what do we get? We get an allylic cation that is resonance stabilized. Because of resonance, it's stable enough to form. We can draw both resonance structures. Like that. And then when the nucleophile adds, it will add to the carbocation. To give you a product. If you do have more than one resonance structure, you would need to consider both and end up picking the one where you get the more substituted double bond generally.